We are so excited. Today we have the first day and the first morning, we have the first pair distinguished lectures. You probably know that the pair organize these distinguished lectures from time to time. And we always have a very high profile speakers with us. And today we are very happy to have Professor Huayong Yang from Zhejiang University to be our first speaker. And some of you might not know PAIR very much. I'd like to just give you a brief introduction. PAIR stands for Purdue Academy for Interdisciplinary Research. So we focus on our daily life, try to improve our living quality here in Hong Kong, in the Great Bay Area, as well as the nation. And PAIR currently has 11 research institutes and 7 research centers, focusing on 3 different areas. The first area is on the sustainable cities, and the second one is on advanced technologies, and the third one is on well-being and human life. So each areas we have about 6 research institutes or research centers, and each research institute or center involve like at least 3 or 4 faculties or schools here. And PAIR currently has over 500 senior researchers. Last year, PAIR has a total internal research funding injected by the university for about $150 million. And PAIR researchers gain another $600 million of external funding. So we publish over 1,000 papers, but that's not our aim. Our aim is really try to produce a lot of impact through our research results. So now I would just like to invite Professor Wang, our Associate Vice President, to give an introduction to our speaker. Thank you.
Okay, good morning. Okay. For us, we expect to celebrate the first working day of the new year with good food, with the hope to store sufficient energy to power our future. Very excitingly, we gather here today to celebrate the new year with another high level of food, a spiritual food that gives us new knowledge, new energy, and also new strength. We are more than happy and honored that the spiritual food and the first lecture will be shared by our distinguished speaker, Professor Huayong Yang. Let me briefly introduce Professor Huayong Yang to you. Professor Yang is currently the Dean of Faculty of Engineering in Zhejiang University and also the Director of CDK Lab. And I want to mention 2 points. I think probably you don't know. Professor Yang is the first winner from the award, I think is Joseph Bramah Award from UK. I think the only one, only Chinese winner, not only in Hong Kong, mainland China, also Europe and USA. And also Professor Yang is the winner from ASME 2021 Robert Koski Medal. The second winner, I think the first winner is Professor Huayong Yang, the president of Chinese Academy of Science. And currently his research interest is hydraulic engineering and recently shifted to biomanufacturing engineering. And also he launched a journal, I think it's biomanufacturing and printing. Okay. With further ado, let's welcome Professor Yang to give the distinguished speaker. Thank you.
Thank you for your kind introduction, President Wang, 李院长、张院长、陈院长 give such a short notice. I'm honored to give a talk about our recent development in the biomanufacturing of functional tissues and organs, exploration and progress. So my talk breaks down into 3 parts. First, about the background. As we all know, the organ transplantation become very typical operation in the hospitals. Even we have a professor in Zhejiang University, the Professor Zheng, he could do the organ transplantation with 2 organs, which set one of the 3 world standard. Now it's in practice everywhere in the world. But we also know worldwide there is a long waiting list for the organs. Because all the people encouraged to their donation their organs during the lifetime, but in practice, particularly Asian countries, because of history, religion, end of the day is still very much short of donors. So we know that more than 2.5 million people are waiting for the right match organs. So there is a big demand for the organs. Yet there is one aspect to meet the demand is to manufacture the tissue organs. Of course, there are very daunting tasks, the challenges facing scientific and technological challenges, because we all know the life evolved on Earth through billions of years. So we, from the manufacturing point of view, first we need accurate design and positioning, fabrication, and also the functional introduction. So the structure of the organs extremely complex, both micro and macro. So there's a traditional way for the biomanufacturing methods. You need to clean bones. It takes about 3 weeks to manufacture, for instance, the largest organ for human is the skin. The skin, 4 centimeter by 4 centimeter takes 3 weeks to manufacture, costs you more than 12,000 yuan. Yet, as we all know, nowadays the manufacturing technological revolution taking place in the world too. First is robotics. The other is 3D printing. So 3D printing, we talk about the metal, non-metal, or bio. Of course, the 3D printing takes about few minutes, 3-5 minutes to print, but the material is biomaterial. You could have a DNA cell, but the functionality of your printed is facing a lot of challenge. So nowadays, the worldwide, the well-established research organization across the world, people are all working on these disciplinary areas, either US, Europe, Asian countries, Hong Kong, and also the financial sector play a very important role as well. So there's a lot of development going on in the world, in particular the past 3 years during the pandemic. We know the science literature has been published advancement. For instance, 2 years ago, Harvard has done this model, the scale for the rotary spinning, whereas Carnegie Mellon University constructed the 3D printing high positioning four-size hearts. Also, Harvard last year has printed the functional artificial muscles being developed. Also, Rice University has been printing use newly digital lighting process method. So all this has been highly focused by scientific community. Of course, in those development trees, the mainland China, Tsinghua University, Xi'an Jiaotong, Zhejiang University, and Shanghai Jiaotong University also play each different roles. So come to the bio 3 printing. So first, we did image data. So it's cross-disciplinary. So we did the image data and digital model to start with. Then we did the material, the BioLink, ink and cells, and then come to biomanufacturing, the Mechatronic devices, also regenerative medicines, which could produce the organ transplantation, tissue repairing, drug delivery, health monitoring, drug screening, and nowadays it's being popular for the food construction. Now people are printing the pork, beef, and Zhejiang University will be printing fish meat. Let's be try out everywhere. So talking about interdisciplinary, so first the basic subject is materials, biology, ME, mechanical engineering, basic medicines, and clinical medicines. So as well as emerging IT technology, AI, intelligent equipment, positioning instrumentation. So there's been 6 steps. First, we need the medical data. Then we build the structure. Then we need the bioink, cells, and 3D printing and evaluation. So worldwide, people has been discussing about roadmap in this research area. At moment, we are in the 2nd stage. So the first stage is already achieved. So additive manufacturing, we could, medical devices has been commercialized. 2nd stage is to set up standard formation. So organ chips have a scaffold contain our cells. The 3rd stage, we will have processing standardized. The final stage will be in practice transplant, tissue organ transplant in practice. Maybe there is 5 to 10 years delay than previously people been discussed. But definitely every week we hear some new breakthroughs somewhere in the world. So lots of happening across the world. So we started in this area 8 years ago. As Zhejiang University is comprehensive university, in the Faculty of Engineering, we have 9 different schools. So starting, we try to do the materials, the biomaterials. There are 2, we need first shape fidelity. We need the strengths, material strengths, and also the biofunctionality, which friendly, the whole material friendly to the cells to grow. So we need both. Traditional bioprinting window, we need to enlarge, optimize the windows. So from the 3D printing point of view, the micro and the micro down scale to the nanometer. The micrometer, we talk about 10 centimeters. So across the whole scale. Material strength from 10 to megapascal, the whole scale for the material strength. Of course, we all know the cell, all different types of cells. It's all involved. So challenging is the position distribution of multi-cell types, high positioning, micro, nano, cross-scale manufacturing, and also cross-scale mechanical strengths for engineering tissues and organs. So for the 3D printing, there are 3 major processes. Is the ink printing, like the printer we normally use. And also the microwave extrusion printing, also breaking down into 3 parts. The nearly field direct writing, coaxial extrusion or suspension printing. Third is newly developed in recent years, the digital light processing. Then it's come to the system itself, 3D printing system itself, and then application, the tissue repairing, etc. So first, let's say the 3D printing process. So when we come down to the injection printing process, there's a lot of ink bubbles. The laboratory I come from, we specialized for the cavitations, fluid power. I was very much specialized. We are one of the top 3 laboratories in the world for fluid power, for injection, for cavitations, the air bubbles or liquid bubbles, etc. But of course, injection printing process involves all this fundamental research, start with mathematical models. Then we set up test rigs to do the experiments to compare with the simulation results. Extrusion bioprinting, of course, as we know, extrusion bioprinting, you can put the force, or you can add electrical force, or you use the pneumatic power in working on the nozzles. So you could testing with this process to manufacture whatever different shapes, different formations you want. And 3D pre-stress printing is involved for the tissues. And there's lots of mechanical simulation we could use before we set up to test rigs to simulate the cell orientation. End of the day, we need printing scaffolds which orientate the cells to grow. So lots of techniques need to be developed in this area. So the devices, the multi-level vascular network, of course, the main blood vessels, it's much easier to design, to manufacture. But it comes to a capsular network is facing a lot more challenge. So we need to go back and redesign the nozzles and also the ink, the hydrogel, the bio ink to constructing every network you wish to develop. So we working on this for multi-level vascular network and observe how it grew the capsulatory networking in very details. Come down to the small micro size, actually cell itself will grow, but you need to orientation to let this happen. So in the laboratory, we did a lot of ultra soft biomaterials, printing in the micro level, terribly small formations with very complex structures. And we add on tracing different materials, see what we could get whenever it's needed. So in this area, we did a lot of study by embedded printing of biomaterials with multiple cross-link method. With different materials, lots of challenge on the processing, the method, as well as the devices, the manufacturing device itself. First, we need to use all this existing printer and say what could do. So with different structure, and you come down to micro, first the micro scale, see what structure you could produce down from scratch. Then we use high positioning, the near field direct writing printing method to print all different formation of scaffolds. The scaffold will guide the cell to grow. And also high positioning near field direct writing applies to different areas. Like we could have the Brussels, the tumor, the small tumor on the main vessels of blood, and the arterial capsular vein could go down to 10 micro or 500 micro scale. So when you could change the scales, then you could put on different application to study. Also, the functional blood-brain barriers the drugs will pass through the blood-brain barrier to actually be effective. Whereas with 3D printing, you could do the organ on chip, looking into in great detail the high density cells you could develop. try to get an idea what's going on when you try to develop the new drugs. And also bionic lung. The lung and heart is most challenging organs at the moment because we not really understood yet the brain, how the brain work. A lot of researchers set up their task to printing the brain cell, yet the organ is out of question yet. But of course, the lung and the heart is most challenging organs. But of course, the people working on this area try to do something in research for the lung and heart. And also the tissues, when you have a structure with different materials, how you construct to design and to manufacture and bring down all this as a requirement for mechatronic devices, the printer itself, or the method, how to use the printer is also the challenge. So the high efficiency stem cells for the liver repairing is, excuse me, it's been used in this area. Back to digital light processing, it's been developed in recent years and it's been very powerful. It could use to construct any formation of the materials, and the scale could go down to 1 micrometer. And to use this digital processing, digital light processing, the process being very critical as well. So on the left side, we have a continuous one go, straight, or you use conventionally vibration method. And then the end of the day, the speed, the surface, is different. It's left side being developed is much quicker, efficient, much smooth in surface. So using the same printer, you could use different way to use the processing. You get different results. So for the dynamic support, the bus assistant DLP printing, again, we tried different stress, different materials, different fluid bioink, and then the outstanding biological function are different. So those are fundamental researches, and also directed myocardial tissues. There's lots of challenge here because for the heart, the cell is vibrate, which has directions. On this side, we working with our affiliated hospitals in Hangzhou. They are specialized for the heart. So the cells contract, and you need alignment. But all the cells, you need facing one direction contract. To develop these techniques, then the doctors could use to repair the damaged heart surface. So all those have a background of requirement from clinical techniques being developed. The bones be mostly commercialized first. Lots of techniques has been used for the bones, the mix functionality, but the soft bones are very critical. It's not been really a large-scale application yet. So a lot of detail still need to be studied, particularly use the DLP processing. And also the microenvironment for the functional regeneration for the cells can really improve the survival rate of the cells when you use different design and techniques to manufacture. So that's the processing part. Then we come to the structure part, the devices. We need a 3D printer. Lots of commercial available printers, but come down to specific subject or project, it's not widely available. You need to somehow adjust these printers. For instance, we put on pneumatic assisted to air blue, so it could manufacture different the micro scale of the board. We could use that to construct any other organs outside or inside. This being for cancer drug screening, we use the 3D tumor array for the drug screen system, the sandwich, putting it together. Excuse me. The bioink, the microscale bioprinting could be used. For instance, the we develop printer which is portable, put in the backpack. It could printing on field, like for the rat, is damaging the skull. You could printing here different patient on rat. So those we come up with the idea so-called the concrete bioink. So to like the concrete in construction, civil engineering, but with the bio using different materials to mix, which is portable. You can carry out in the field. So to do whatever is need. Then come to the 3D printing systems, the printer, different projects need a different printer, which are not commercially widely available. So we developed the portable with not so much on the positioning side, but reliability. Of course, we also try to develop a new, highly the positioning 3D printer, which will come up the highest positioning 3D 6 level of printer we developed in the past 5 years in our laboratory. So XYZ is 6 nanometer nanometers, and Z is down on micro. Everything, the whole system is all produced, manufactured in Zhejiang province. Of course, we have come up with new ideas. We have the Geneva Invention Patents Award. With this printer, we can control 6 nozzles with a high precision. So in a very critical small area, it can construct 3-dimensional whatever type shape of organ you wish to print. So of course, we also developed a much simple, easy use the printer together with BioInc. Professor Huayong in my group, he developed this, and also BioInc spin out in Suzhou. They formed a small high-tech company. Now they produce the BioInc hydrogel. They sell to 1,000 universities, 3,000 laboratories. The market share now is 70%, but mostly on the research side. But those simple but easy to start with printer and hydrogel, or the BioInc is a kind of a package. Of course, I introduced why we have developed a play with our graduate students in laboratory, the printer, the processing, how you do different manufacturing methods. It has to come down to applications. Applications, of course, the skin is most in the clinical need for the skins, not only for medical use, but also in the cosmetic industry. Huayong, the French manufacturer, they develop their new cosmetic products. They spend 4 billion euros a year. And yet there's agreement that we cannot test the new products on the skin of animals. So now we need artificial skin to try out. So there's an immediate market for it, beside the medical use. But for skin itself, it's very hard. There are 7 different layers of the skins. The sixth skin of a human is 200 micro. Yet for the skin, 7 different layers, there's vascular, the blood, liver, and the hair as well. So lots of a challenge for this. How we introduce this, there's lots of research going on this area. So we also print the 4 layer of skin and compare with the commercial skin and see how they win. The cut wins has been sold. So it's proved more than 70% increase to heal the wounds. So there's lots of going on for the skin side. Also the vascular size for thickness of skin for the rats, rabbits. As President Wang visited Zhejiang University, our new campus, the number of animals is more than human. in that campus. So we could easily access to this animal laboratory. They look after the animal. They ask our graduate students in ME don't have to look into the rats, rabbits, etc. So they're special experts on that. So we did a lot of animal tests, the trials. So we do get some progress and attracts attention by CCTV1, CCTV10, which report on the science and education. The other is dentist. We know, excuse me, there's a market is also exploration is booming in China, in mainland because of economic development. People are very ready to pay for going to dentists. All those the restoration film is all imported from Europe or US. Now we looking into this film market. Previously, we developed all the techniques, the printers, and now we're focusing on print the films for dentists, the oral restoration film. We did a lot of trial first in laboratory, published papers, and lately we spin out. And there's new company actually try to get passed for FDA China, get permit to the manufacturing for the market. So those film are actually in great detail, have to compare the existing products. We have to try a different method, a different approach. Breaking into a market, you have to have a new advantage of a product, not following up our counterparts in the West. So we always try to come up with new ideas, new approach. The other application area is spinal or injury. We know there are up to 500,000 patients worldwide has a spinal injury in the world, which are young or middle-aged patients. So this causes so much of a pain, not only for patients, but for their families, for the society. So how to develop the artificial spine code to help out, to repair. Lots of techniques have been looking into say how we could come up with some new solutions. Here is the animal trial. The up is control group. It doesn't repair at all. Down, the functionality has nearly restored 30%. So making some progress. And yet for the liver conducts, because of injury accidents, car accidents, if you're missing more than 5 millimeters, you can't grow yourself. You have to repair. And there is $11 billion US market here. So how to develop this lever system? The previously smooth lever contacts on the left side is typical. We come up with grooved lever contacts. They have a microstructure inside, which helps the cells to grow. So we use liver repairing first on the rats, introduced the groovy, different size, different dimensions, using different cells. You see the left side, the rat, doesn't feel the heat or the lighting. On the right side, is repaired, the liver system. So for this liver conducts, we look into great details. This potential, how we are developing. First, we come up with idea. There are two layers. Inside the layer is more friendly for the bio-friendly for the cells. Where out layer, it has mechanical strength because you have to hold different strengths. So this comes down to develop the devices. It has to manufacture simultaneously inside layer and outside layer. So you can come up with the Mechatronic devices. Again, the micro grooving in internal layer, so you add on more complexity. So we look into the great detail, the liver cells regeneration, with different materials, different manufacturing printer, see how it is repaired through animal trials. And then we come up with three different generations of a method or products. It's all come different timing areas. The grooved liver conducts, biolayers, is all on the different trial. But at end of the day, in 7 years, these three products will be on the market commercially largely available. But the first generation may be in 3 years. So this is liver conducts application. Come to the dental implants. Again, everyone at our age always have the tooth implants. And the exponential is also booming in mainland China, like in Hong Kong or Europe, US. Previously, all these players in the market is from mostly Europe and US. Is two dentists from Germany and Swiss developed this idea and products. So companies is mostly from Europe. The traditionally method, first you took the tooth out, and then you need 3 months to 6 months. The tooth bed settle down, then you implant, like ME school is flat to get in, then 3 or 6 months later, you plant installation. Then you use the crown installation. The whole process that takes half a year to 10 months. Normally you need 5 to 10 times to visit to your dentist. Some good specialized hospital dentists need 3 visits. That's shortest one. But our idea is wallet print. Before you took the tooth out, you print according to the later shape. So that one, again, we put on great details. The microstructure could build into. We try to cut down the timing by half. So when you took the tooth, you print it and plant. So simultaneously cut the whole thing by half. Without going into great detail, all the material and techniques, everything else is all in managed channel. We try to get a local supplier for material, also get approval. So lots of gradients in plant microstructures. So could, with the complex geometries. Of course, this technique has been developed in past 5 years. We use the rabbits, New Zealand rabbits for the trials. Then the dogs, the beagle animal dogs, their true force is much strong. So we work on more than 2,000 different dogs, 5,000 rabbits, and developed all the different techniques, say the overall effects and compare with the traditional method. So this recently also been spin out. There's a specialized company. They are doing this outside of a university law and is trying to get approval, start again from scratch, from material, get all the approvals before going to the clinical trial. I think this year they will be doing clinical trial more and probably 3 years they will be commercially available. So overlook. First, we are trying to do similar in structure, resemblance informs the organs. Most challenging part is the functionality. Resemblance in spirit, the functionality is most challenging. We need to set up new evaluation method, standard, and it has to be internationally approved, at least from a region and to a country. So their association, which I'm also play a part in managed channel, we try to come up with different standards because it's all new techniques, new products. We set up new standards for this. So in this area, 5 years ago, I started a new magazine called Biodesign and Manufacturing together with Professor Cui from Oxford University. So it's quarterly magazine. In less than 2 years, we've been SI indexed. And at the moment is 7.9. I think in few months, it should be something close to 9. So we come up with a new way to run the journal. We have a managing director, Ms. Zhang. She's very professional, and 2 professional editors, but yet we have a very active academic editors. So we could give any proposal less than 40 days being approved in printing. So this runs very fast. At the same time, 2008, we launched an international conference. on biodesign, manufacturing, and biomaterial. First in Hangzhou, the second in Tianjin. Then we was decided to go to Portugal, Oxford, but then pandemic came and stopped. But last year, somehow we renewed our activity. This time it was in US, in Singapore. We have delegates from 12 different countries, 64 universities, 5 hospitals, lots of doctors. It's more than 160 interdisciplinary experts. So we had a good time in Singapore, and we decided going to continue to run maybe in Asia, maybe in Japan this year, but next year to Europe somewhere. So this is a really very active area. We met people from all different backgrounds. So it's also, we run the forum for young researchers starting 2 years ago, 3 years ago, 2021, 22, and last year, just in our school, the third one, there are more than 4,000 viewers on the internet, people following this area, because every week we reading the proposals of papers. There's so much of a new progress in this area. So there's a we have a cross-subject collaborators. Professor Zhang from Harvard, Professor Wang from Florida, Sherry from Cambridge, Oxford Tree, many Shanghai Jiao Tong University, Xi'an Jiao Tong, and Tsinghua University, our affiliated hospitals, many researchers, we really try to work in together. So everyone else, particularly in Hong Kong, there will be lots of opportunity because you have a very good financial market here. You get the investments, spin out the whole structure much easier than mainland. Again, since 30 years ago, Zhejiang University has been partner with Hong Kong Political University. So hopefully we will working together more in the coming future. Thank you for your attention.
Very wonderful talk. I think the topic is very broad, covering from heart, lung, cord, dental. I think in spite of the very broad topic, underpin a very common technique, plating. So now it's time for questions from the floor. Professor Chen.
Thank you, Professor Yang, for a very excellent presentation. I learned quite a lot, although I'm really outside of this subject. I have a question. You know, traditionally, we also use tissue repair and also animal organs to cure the disease. Compared with the artificial tissues you are developing, can you just give me some comparison of the pros and cons of those different way of treatment?
Yes, Professor Chen, yes, there is lots of challenge. When printing the tissue, as I mentioned, it won't take time, 3-5 minutes. but the tissues you printed, if it's fed to the animals, not mentioning the humans, is lots of challenge here. To set up the cross-disciplinary research team at the beginning are really hard. Even for us, for Zhejiang University, we are in same umbrella. When we talk to the doctors, they are extremely busy. Low timing. It's okay for talk, for discussing afterwards. They are so busy. So the professors, it's not easy to work. And then we found out maybe postdoctors it's easier. So the tissues it has to be specified. When the clinical doctors ask tissues, they're extremely high standard. You need all the approvals. Get all this approval takes 8 years, typically, 6, 8 years. So before being the clinical use, so we has to develop step by step in laboratory, training graduate students, even for medical graduate students, because average the graduate students from medical science, the biomaterials, they're consuming 100,000 yuan a year, typically. So then the standard is not that high.
So can you predict when you could use your technology in a clinical trial?
Yes, we are being printed for the tooth implantation.
Yes.
A technical trial, that's easier, but with the cells,
Yes.
it's difficult. It's not immediate future yet, but it's all going through the animal trials. And it gets proven it's not so easy.
Thank you.
Yeah, any other question? Of the mic?
Thank you, Professor Yang, for a very stimulating talk. I have two questions. One is about the dental implant. These multiple clinical steps for the dental implantations is very interesting. But if you look at the orthopedic joint replacement, right, it's always one step. You create the cavity, you input the implant in the same surgery. I wonder what is the critical needs for the original multiple steps for dental implants? I think your approach is very reasonable. Why this was not achievable in the beginning? That's my first question. My second question has to do with your comment on the functional evaluation. This is really so important. I'm very pleased to hear that your lab and other labs in the mainland are working on this, and this is so important. It's so easy to publish with some minimal evaluation, but the magic is at the end. Okay, the functional, probably in the macro scale, as well as in the multi-scale that you mentioned. And you mentioned about the consistency challenge, the challenge to biofabricate with enough consistency. And I would think that the biological constituents sometimes are quite tolerant. Sometimes it may not be as tolerant. It may vary from tissue to tissue. Some tissue may allow some crude in materials to be inserted, and then they could work with those crudeness quite well. May not be in other tissues. What do you think of the most challenging, in terms of consistency, in terms of your manufacturing resolutions?
That's very important two questions. First, the dental implants. The previously techniques is a flat screw with one surgery. You put in first. You sit down after a few weeks, they do the toe. Then put on crown. That's why you need at least 3 times visit. I think it's 3D printer. The technology, 3D printing has been advanced compared to say 20 years ago. Nowadays, we can plant the before you taking the tooth out, you make X-ray and take the lateral shape and the screen, and then you're printing before the surgery. When they take the bad tooth out, then you put the implantation at the same time in one surgery. So particularly with the last tooth, sometimes the last tooth might have 3 in regular shapes. Nowadays, the printing techniques can produce very precisely.
It was a geometry issue. It was a
Yes.
micro, okay.
And geometry dimensions on the surface of implantation, we could play on lots of techniques. So which the implantation would fix there, they won't get loose. This first question. The second question, yes, functionality. Functionality is so important. People working on this area always have lots of arguments and debates. Once I held a conference in Hangzhou. It's organized by the Nature Science Foundation of China with pharma engineering parts, medical part, and mathematics, physical mathematics part. 3 young researchers, we come together and try to discuss. And the whole meeting after the conference meal, we sit back again in the meeting rooms and still debate talks until midnight. The whole hotel tried to shut us up. There's so many issues involved. Yes, you are right. The tissues, a different cell of tissues, sometimes you think they don't work together, but somehow you introduce new tissues, all the cells seems compatible. They can grow very harmoniously, but some other times they refuse. So it's very difficult to tell before the experimentation. This need to be really looked into. There's lots of challenge in this part. If we can get through this evaluation, then we could come up with standards, and they will speed up the whole processing of the commercialization. There are so many techniques, products has been developed across the world. Majority, I don't know, more than 90% is all animal trial. It is the evaluation, how we evaluate, how you see the particular life cycle, duration, how you set up standard, how you check it, how reliable when you set up standards.
Okay, any other question? We do also have question. Okay, you start first.
Thank you, Professor Yang. Your speech fulfills us with the confidence in fighting the future many disease. And so I have 2 questions. So at the end of our body, we have many capillary vessels, which only allow one single blood cell to going through, and we exchange nutrition, oxygen with the cells and the blood cell. So my question is that I noticed you showing some results say we can already 3D printing the capillary vessels in 2D form. So my question is that can we print all the enough capillary vessels in all kind of the organs? Because if the capillary vessel is not enough, they will forbidden all the cells to get enough nutrition from the blood. And my second question is that I forgot. Maybe just the first question. Thank you.
Okay. Yes, that's a good question. That is newest progress within our group. We developed the capillary, the blood vascular network. Yeah, at the moment, it has to be specific. It has never been achieved before. So we try to use different cells aim on different organs. At the moment, it is very limited at this moment.
And I want to know, say, if we also when we use the hydrogen to doing the 3D printing, do we put the cell in hydrogen in front of before the printing conduct?
Yes.
Oh, and after we finish the 3D printing, we grow the cells in the hydrogen, and if the cell they are multiple growth and increase their number, will they block the vessels after that? Afterward?
Yes. The first hydrogen you use the bio-ink you mix with the cells, stem cells with the material. Then you do in the printing. The first you need to look into through the printing process. What's the survival rate of the cells? Then you have to adjust all the parameters of your printers and also the whole process. You want to standardize the process and to see the whole active rate of the cells. Yes, with the cells in the hydrogel is facing a lot of challenge. Yes.
Thank you very much.
Professor Yang, there are also some online questions coming up. The first one is currently a number of poly researchers have been used caffeine power and also the tea leaves for 3D printing. What's your view towards their potential for application in biomanufacturing?
Sorry.
They use coffee power and tea leaves for 3D printing. What's your view?
Coffee power.
Yeah. Coffee power and tea leaves. In poly, we use it for printing.
This is long metal printing. So first is metal printing. The techniques has been developed very much mature now. And the long metal is still need looking into in the great details. Depends on the applications, the specific application, which area you look into, and also if you want to add it on the cells a lot. This area, non-metal area materials, is not so mature. like use a metal powder, it's much more confidence. With those no metal, the coffee powder and tea leaves, then depends on where you use for the specific application.
Okay. The second one is more general. Biomanufacturing is a highly disciplinary topic. What are the major barriers in collaboration from your own experience?
Yes, so lots of barriers cross integrate research. Every university try to encourage, set aside the fundings, like Professor Chen was saying. Every university management is set a budget for disciplinary projects, but it always lies at the beginning to start with. Then people talk about the goals, specific aims, then come to the management side, the graduate students. As university community, people say, these students, you cross the subject. When they're at their graduation, what are evaluators you send to? Do you send to the ME engineers, ME background professors, or to the medical professors? All have different standard for a PhD thesis. It's not so easy when you have a joint supervisors. But in practice, different school say, okay, this students belong to ME, then they come to ME, or that student goes to material science. But the whole process to the students evaluated their thesis have some different background of our researchers. Their standards are all different. So it's very challenging. So really working together, the different background persons with their PhD students, how really professors really can talk at least monthly basis. Then we really has cross the subjects, cross-disciplinary research. Otherwise, everyone have different goals, different traditions. It's not easy, but if you insist on doing this, after 5-6 years, and then you always come up with some new results which you would never expected beforehand. I had this experience before. So working with different researchers from different backgrounds, at beginning is terribly difficult. You ended up the argument, then maybe in tea house, then you have a laugh, then go back, try to think, or maybe have a beer. Then, but after a while, you argue, debate, and then somehow you found a solution. People have a different challenge questions always. After a number of years, you get used to it. So people have a different method. Then they will come out with really unexpected good results if you insist on doing this.
Okay, very good. Any other question? Okay, as I mentioned early, Professor Yang, won 2 highest awards in hydraulics engineering, one in UK, another one in USA. I think listening to the seminar, we really enjoy the passion, the knowledge, and also the insight learned from Professor Yang, moving from traditional hydraulics engineering to emerging biomanufacturing. I think Professor Yang really set a good example for us, right? How to cross boundary to live the world. hopefully, Prof. Yang can continue visit us. I think next step really we have functional tissue and organ for us to live longer. And also, as I mentioned, today is the first working day of the new year. Wish all of you, all over the field, with good health. Of course, the health enabled by printing. Okay, good health, good warmth, and also good wealth. I think the wealth not only in money, but also the wealth in knowledge. Thank you very much.